So guys, my name is Stephen Rennick. I'm a geologist at IGO and I'm presenting to you from Perth in Western Australia. And tonight we're going to be talking about the camp scale structure and stratigraphic controls on the Nova-Bollinger intrusive complex and how we map those controls in 3D seismic data and how we target, I guess, in an exploration context using those controls. So this work is the result of a large re-logging project that a group of us did across the deposit through 2018, 2019, and a lot of deep diamond drilling and 3D modeling since then. So before I get started, two quick acknowledgements to John Standing and Mark Munro, who are structural consultants from Model Earth, who we did this work with, and a lot of the structural work weighs pretty heavily on theirs. And Josh Coombs, who's currently running the 3D modeling at for IGO, and he helped with a lot of these slides. So second slide, just a cautionary statements and disclaimer, IGO being a publicly listed company on the ASX, please don't use this talk for investment advice. So starting off, regional geology and what's kind of, I guess, important for this discussion. Nova-Bollinger is located in the southeastern part of the state of Western Australia. It's about 700 kilometres east of Perth. And geologically, it's hosted in the Fraser zone of the Albany Fraser Orogen. So the Albany Fraser Orogen is a Paleoproterozoic to Mesoproterozoic belt located along the southeastern margin of the Yilgarn Craton, which is shown there in grey. So the Fraser zone outlined in dark green there consists of voluminous gabbroic sills and granitic intrusions, which have been placed into a sedimentary basin called the Snowy Stand Formation. And that emplacement has driven high-grade upper amphibolite to granulite facies metamorphism across the belt. So there's a suite of mineralized intrusions which are interpreted to have been emplaced into the belt slightly later than the bulk of magmatism, and they're in place during synorogenesis and syn granulite facies metamorphism. We have mineralized nickel sulfide occurrences spread across the Fraser zone, so over a 350, kilometre range, shown there in little white dots. But Nova-Bollinger is one of 4 sites of significant mineralization and the only operating mine in the belt to date. So we'll take a zoom in to the local scale geology, and we'll kind of work around the geology of the surrounding area around Nova-Bollinger. So I've got, a schematic map of the solar geology interpretation here on the left-hand side, and a nice long section which I've taken kindly off the next presenter, Ben Cave, outlining in detail the igneous architecture. But basically, Nova-Bollinger is associated with the pipe-like intrusion, which we call the lower intrusion, and it's located here and located along here. It's associated with the much larger sill complex, which we call the upper intrusion. But the real key at this scale is that that's a part of a much larger mineralized intrusive complex, or intrusive complex again. So we have what we call the western intrusion, which runs into Perseus, into Alara, and then we have the Hercules and the double dipper intrusion. The stratigraphic architecture consists of 3 different lithostratigraphic domains at this scale. We have what we call the Western Mafic sequence, the Nova Mine sequence, and the Eastern Sediment sequence. And these 3 different lithostratigraphic domains are separated by steep domain-bounding shear zones that often are filled by potassic orthogneiss intrusions. So we're going to take a long section through this, a northwest, southeast long section through this local geology, and look at some of the seismic data now to get a better picture in 3D. So we've got a little schematic diagram on the right-hand side. We're looking to the northeast, and then this is a section through our 3D seismic data. And we have 3D seismic data, lucky enough, across basically our whole camp. And what you're really looking at here, apart from a whole bunch of squiggly lines, is variations in acoustic impedance. And acoustic impedance, luckily enough for us, really maps lithology and structure quite well. So I've overlay now the interpretation from drilling and seismic insert. You can kind of get a bit of an understanding for the 3D architecture here. So the key kind of controls at this scale is that we have these two major faults called the Jupiter fault and the Nova fault, and you can see the relationship between those. And we find that our mineralized intrusions are either focused along those faults or within this sequence called the Nova-Bollinger sequence. And that gives our team, I guess, a fundamental targeting element at this scale, because we can map these three different lithostratigraphic domains up and down the belt. At the next scale, we find that the intrusions are commonly in place within the meta-sediment sequences, or at the boundaries between those. But one thing which is unique about Nova-Bollinger, which is located and associated with this pipe-like intrusion here, is that it still remains the only site of, I guess, the only economic ore body. But the difference is this intrusion has a pipe-like geometry. It's got strong focus, whereas a lot of the other intrusions that we have are much more sill-like or much larger dike-like intrusions. So I want to take a look at some of the two kind of key controls, what we think forms that pipe-like geometry, and then how we can target that. So we'll start off with stratigraphy. I've got a very schematic stratigraphic section there on the left-hand side. I want to take you through some of the host stratigraphy around Nova-Bollinger. So that upper and the lower intrusion are located here, with the Nova ore body associated with that lower intrusion. So in the hanging wall, we have a large package of metasedimentary gneisses, which really range from graphitic, sulfidic peelites, shown here, through grey wackies, peelites, semi-peelites, and sammites. In the footwall, we have a sequence of mafic gneisses, mafic granulites, and felsic orthogneisses. And the key things at this scale is that the hanging wall sequence and the footwall sequence are large, quite monotonous, and consist of, I guess, large, quite simple packages. Whereas the sequence where the Nova-Bollinger intrusions are placed into is quite different. It's got a lot of small intercalated units, and the units are quite different to what you see throughout the rest of the sequence. We have a lot of reactive kind of units, marbles and calcarenites, quartzites. We have iron formations which are loaded with sedimentary and other kinds of sulfides. And then we have these units which are called metaconglomerates, although the prolith of those is quite debated. But the important things at this scale from a targeting or from an exploration point of view is that this horizon, we see intrusions at this horizon commonly at different prospects without the AFO, so we know it's significant for focusing intrusions. And we think the reason why it's significant is that it's at the contact between two quite large packages, and it likely represents a rheology contrast and a different kind of density horizon, which channeled magmas during the initial emplacement into the sedimentary basin. And the fact that the horizon is loaded with sulfide-bearing rocks and reactive rocks such as marbles and carbonates likely forms the local chemical changes to the magma to promote, large volumes of sulfide generation and formations of those ore bodies, which we don't see in other parts of the sequence. So the second major, I guess, set of controls that we infer at this kind of scale is the structural controls. So the Albany Fraser Orogen has seen two major deformational events. So it's definitely a little bit of a mess trying to figure out the structural architecture. That's why there's a lot on this slide. But basically we have 4 generations of folding. First generation of folding is associated with the development of this penetrative S1 tectonic foliation, and then we see that refolded three more times. So in the F2 folds, we see them at the core scale, and they're associated with this northeasterly plunging recumbent folds. And they're also associated with a strong northeasterly plunging mineral stretching lineation. And that northeasterly plunge will become important in the next slide. We see these core scale folds refolded again by upright to inclined, open to tight, coaxial folds. But these are a much bigger wavelength. And then we see the D3 folds folded again by folds of a perpendicular nature, and again another upright fold. So these 4 generations of folding form 2 different kinds of fold interference patterns. And I've got a schematic down here for the first one. We see type 3 fault interference patterns folded again and to form type 1 fault interference patterns. And the structural data I have on the right-hand side here, the main takeaway from that is that you can see the foliations, the gneissic banding, and the fold axial planes, all folded around a shallow northeasterly plunging axis. And the fold axial data and the lineations also show that. When you look at the F3 fold hinge data, you can see, two different populations, and that can be explained by folding around an F4 fold hinge. But the most significant thing to take from this slide is that the bulk of mafic magnetism was in place during or pre-D1. And we see that because we see it transposed into that original S1 fabric. Whereas the Nova suite was in place slightly later into the D1, D2 architecture, either during D3 or Sim D3. And that becomes important on the next slide. So if we try to show that graphically, we can show that the F3 in red and the F4 fold axes in orange create the double plunging sim form in which the Nova-Bollinger intrusive complex is hosted in. But most importantly is that F2 fold architecture shown by the yellow traces, and you can see those there. And the reason that's important is that linear control is the linear control is the key control in forming that pipe-like geometry of the Nova-Bollinger channelite. And we know that pipe-like geometry gives the intrusion that focus and allows it to form the high volumes of magmatic sulfides that we see here, as opposed to the larger seal or dike-like intrusions where we see in lots of other parts of the Nova camp. So lastly, I just wanted to, show how we translate that into a targeting framework as an exploration team. So this is another snapshot of our 3D seismic data section here. So this is to the north. This is to the northeast of Nova-Bollinger, located here, again, looking northeast. And what we started doing is that we started recognizing and mapping out that large F3 fold architecture and realizing that the large intrusions manifest as lows in the 3D seismic data. So you keep your eye on locations like this, locations like that, and then down here. And as we've progressed, we've started to get confidence in targeting F2 fold architecture and those smaller, more dynamic intrusions in locations like that here. So if I put on the solid geology interpretation over that seismic data now, and this is all from drilling, and you can see the depths here, we're targeting at 1 to 2 to 2.5 kilometers. And then we've identified these large intrusive complexes which are blind at the surface, and these more focused intrusive complexes, such as Orion. And then I've included some nice sulfides from these 3 intrusions that we've been intersecting and we're currently drilling out today. So basically that's my talk. Happy to answer any questions. Hopefully I've given you a bit of an idea of how we can use 3D seismic data in nickel sulfide exploration and some of the what we think are the principal controls at the camp scale on the Nova-Bollinger ore body. Thank you.